Welcome. Let me introduce myself shortly. I'm Frank Buckler. I'm from my profession, I'm electrical engineer. Later I did my PhD in marketing research, where I developed a method called NEUSREL. So that was the first name, and it's today the name of the software, which was a result. And then there's another name, Universal Structure Modeling. This is more a name for methods which do a similar job as NEUSREL. So it's more like a methodical group. We introduced this in a paper in 2008 where we described the principles of universal structure modeling. So a quick warning, I have only two equations in this presentation, because I don't like equations and more pictures. So that's for the first warning. And to start a little bit easy, I've made a kind of a comic strip which pretty much explained what NEUSREL universal structure modeling is for. So it's just 2 minutes, and
you NEUSREL for these findings, and you live happily ever after.
So that's a small commercial, but basically the main takeaway, or the main takeaway is that today we try to fit real-world problems into our models we have. Our models imply assumptions about linearity, independence of drivers, and so on. And we tend, in management science, I'm speaking about management science, marketing science, we tend to press everything into this model. But actually, we should more focus on how reality really looks like, what the properties of success driver really are. So a good metaphor for that is this. Typically, we have very good hammer, the hammer getting better and better every day. But if you have a hammer, every problem you have looks like a nail. But it might be a screw. Yeah? So we should apply methods which first find out, is it a nail or a screw, and then adopt itself to it. And the issue is, often in reality we don't know if it's a nail or a screw. Yeah? We need methods who help us to find that out. So to become more specific, what are the limits of structural equation modelings today? First limit is it assumes linearity. The more, the better. And if you're clever, you make a quadratic term or so to a driver, but then you assume a certain functional form, and you assume that a specific driver has this nonlinearity. So you have to know the form and which driver is nonlinear. But in reality, we don't know. The same applies to independency. That's a typical structural equation modeling. You always assume independent drivers. And if you're clever, you introduce product terms, but then you again need to know which terms and which drivers interact with each other. When you have 20 drivers, you have 400 possibilities of interactions. And you then blow up your model until you cannot compute anything. So basically, again, for the standard approach, you need to know up front not only which variables interact with each other, also which kind of interaction, because the product term is only one kind of interaction. It's logically speaking, it's an AND interaction. There are OR interactions, exclusive OR, and so on. There are many more possible interaction forms. And as long as we don't know how the reality is looking like, we need methods who find out for us. Another issue is the scale of the variables. We have, for instance, we have sex, or we have other nominal variables, or binary variables, and we would like to include that in a causal sense, all in one model, not splitting model and do group comparison, because this is not multivariate analysis. It's just a bivariate comparison. So we would like to have a holistic model where we can put all kinds of causing variables or interactive variables into it. And also, there are limits in exploration, because that's why conformatory methods are very popular, because if you put all kinds of variables in a model, it inflates your degrees of freedom, and you are more likely to get also nonsense results. But we need this property, because we don't actually know often which variables truly have impact on our target. So what is needed is, again, a method that can explore where nonlinearities take place and which kind of nonlinearities. We need a method which explores interaction effects and where they are and how they look like. And we need a method that is more flexible enough that you can input also bivariate method, bivariate nominal scaled variables. Why? Because the model needs to be holistic to have no spurious findings. Yeah? Because that's the main. That's why we apply multivariate methods to really find out which driver causes which one. That is why we also need techniques that have regulation techniques. Regulation techniques are meant to enable the method to be more explorative. So you can impute more variables, and the method tries to reduce its own complexity. That is regulation. And it helps us to incorporate more variables and find out which one truly have an impact. So, and the universal structure modeling is basically an answer to that, what we need. And it works like following. So first of all, we have the measurement model, right? So we compute the latence. In NEUSREL, we initialize the system using principal component analysis. And you have the option to use a nonlinear principal component analysis. You can do that with specific neural networks, so-called bottleneck neural networks. And then we have the structural model. Yeah? First measurement model, then the structural model consists out of several regressions. So for every endogenous variable, you have a regression model. And that is what we do. And in the third step, you iterate that. So you can, with a structural model, you can update your latents. With updated latents, you can update your loadings. So this is basically also the idea of partial least squares. Yeah? And with universal structure modeling, we built on that. But we changed two things. First, we use, instead of linear regression, which is always assuming linearity and independence, we use a universal function approximator. So that are techniques for machine learning. You know them under kernel methods, for instance, so support vector machines, or neural networks, the same class. They do basically nonlinear regression, and they are flexible enough to build any kind of relationship using the data at hand. And by using these machine learning techniques, we are able to model and to capture the nonlinearities which are in play, the interactions which are in play. So they discover, they explore these properties out of the data. So there's only one thing missing now. I have a nice model, but I don't know how latent 1 impacts latent 3, right? But this is what we want to know in management science. We want to really understand the separated effect of this on this. And you cannot find out by showing a scatter plot. Is this on X and this on Y? This does not show you the impact of 1 on 3.